Hi there, Miss Barber here. This lesson is titled Expectation. We'll explore. As an experiment, you toss a fair coin 3 times to see the number of times the coin lands heads up. What might be a good expected number of times the coin lands heads up? Before we answer that, let's consider the following scenarios. If you toss a coin 100 times, what might be a good guess on the number of times the coin lands heads up? Did you guess 50? How about if you toss it 10 times? 5 is a good guess. 6 times? Heads up 3 times would be a good guess. And how about 4 times? Maybe twice? Notice that for each of tossing the coin 100 times, 10 times, 6 times, and 4 times, our good guess on the number of heads up is half the number of tosses. After all, with a fair coin, the probability of heads up or tails up is a half. Now, how about if you toss it 3 times? For the toss of a coin 3 times, knowing that the probability of heads up is a half, we really want to say half the number of tosses, or 1.5 times we get heads up. Mathematically, this is correct. It is the average or mean, even though it's not in the real world possible. In this lesson, we study expected value, which is a mathematical process that uses probabilities to determine what to expect in various situations in the long run. Mathematically correct may not always mean realistically possible. Even so, expected value does give long-run averages, and that can be very useful. Expected value. The long-run average is called an expected value. It is a mathematical process that is used to determine what to expect in situations that involve probability over the long run. Expected value may be used to determine premiums for insurance policies, weigh the risks versus the benefits of a business venture, or indicate to a player of a game of chance what is likely to happen if the game is played repeatedly. To compute the value of expected events, consider the value of each event x and its probability p of x. The expected value e of x is computed. E parentheses x sub I is equal to the summation as I goes from 1 to n of x sub I times p of x sub I, and then it is expanded. The standard way to compute expected value is simply to multiply each possible outcome with the probability of that outcome and then add the products. Example: an automobile insurance company has determined the probabilities for various claim amounts to the nearest $2,000 for drivers ages 16 through 21 as shown in the table. Calculate the expected value and describe what this means in practical terms. The table has one row labeled amount of claim and the row below that labeled probability. The likelihood of $0 of claim is 0.7 or 70%. For a $2,000 claim, the probability of that is 0.15. For a $4,000 claim, the probability is 0.08. For a $6,000 claim, its probability is 0.05. And for both an $8,000 claim and a $10,000 claim, the probabilities of each of those is 0.01. Let's compute the expected value. We do that by multiplying the value with its probability. So we'll start with 0 times 0.7. The next one we'll add 2,000 times 0.15. The next would be 4,000 times 0.08. The next one, we add 6,000 plus 0.05. 8,000 times 0.01. And the last one, the largest claim on this table, $10,000, and the probability of its likelihood is 0.01. Multiply this out using your calculator. The result is $1,100. What does this mean? This means that in the long run, the average cost of a claim is $1,100. This is the least the insurance company should charge to break even. Example: a box contains 6 tickets, each numbered 0 to 5, and each of the 6 tickets is as likely to be selected as any other. A player who bets $1 on any given number wins $5 and gets the bet back if he draws his chosen number. Otherwise, the $1 bet is lost. Part A. What is the expected value of the game to the player of the game? Let's begin by identifying events. I'll let A be the event that the player gets his chosen number. Now there are 6 numbers, he chooses 1, so the probability that he gets his chosen number, P of A, would be 1 out of 6. The complement of the player getting his chosen number would be the event that the player does not get the chosen number, and the corresponding probability of the complement would be 5 out of 6. There are 5 of those numbers he did not choose. Let's draw a table. I'll label the first entry the gain or loss, and below that will be the probability associated with it. If the gain is $5, the probability that he would gain that is 1 out of 6. The other possible event is that he loses the $1, and the probability of losing the $1 is 5 out of 6. Now we have the information necessary to get the expected value. We will multiply the outcome with the probability, so 5 times 1/6, and add it to the loss of $1 times 5/6. The result is 0. The expected value of the game to the player is $0. We often call this breaking even. Part B. A game is fair if and only if the expected value equals 0. Determine if this game is fair. Well, the expected value of this game is 0, therefore the game is fair. Part C. What are the odds in favor of winning this game? Recall how to compute odds in favor. It is the ratio of the probability of the event divided by the probability of the complement of the event. We computed the probability of A as 1 out of 6, or 1/6, and the probability of the complement of A is 5/6. Therefore, the odds in favor of this game is P of A divided by P complement of A. The numbers are 1/6 divided by 5/6, which simplifies to 1/5. Thus, the odds in favor of winning this game is 1 to 5. Example: the annual premium for a $5,000 insurance policy against the theft of a painting is $150. If the empirical probability that the painting will be stolen during the 1 year is 0.01, what is the expected return from this policy to you if you take out this insurance? Let's identify our events. We'll let A be the event that the painting is stolen. The problem tells us that the probability of that likelihood is 0.01. The complement of the paint being stolen is that the painting is not stolen. And the complement, the probability of that complement is 0.99. Now we have enough information to set up our expected value table. We'll begin with your payout or your expense and the probability associated with it. Think about this carefully. If that painting is stolen, you will get a $5,000 check from the insurance company. However, you've already paid $150 for it, and that $150 will not be returned. Thus, the payout is only $4,850, and that probability is 0.01. You love this painting, and so it costs you $150 a year to insure it. The probability that it's going to get stolen is 0.01, so the probability that it's not stolen is 0.99. Let's construct the expected value. That's going to be the payout times the likelihood, so $4,850 times 0.01, and we'll add that to your premium payment, which is $150 that you pay, and the likelihood that it will not be stolen is 0.99. Compute this using your calculator, and you get that the expected value is negative 100. How do we interpret this? We interpret it this way. The expected return of this policy to you is a $100 expense. Example: American roulette wheels typically have 38 equally spaced slots numbered 0, 00, and 1 through 36. A player who bets $1 that an odd number comes up, 0 and 00 are considered neither even nor odd, wins $1 and gets back the original $1 bet. What is the expected value of this game to the house? And how about to the player? Let's identify events first. I'm going to let A be the event that it lands on an odd number. Let's think about that. They're numbered 1 through 36, and half of them are odd, so we've got 18. However, there are 38 equally spaced slots, so the probability that it lands on an odd is 18 out of 38. The complement of it landing on an odd number is that it does not land on an odd number. So the probability of that complement is going to be 20 out of 38. We have enough information to construct our expected value table. I'll draw a horizontal line and 2 vertical lines. I'll label the first entry as your gain or loss and the probability of that likelihood. If you gain, that's $1. And let's go ahead and reduce 18/38 to 9/19. And the loss is you lose $1, and we'll reduce the probability 20/38 to 10/19. Now we have enough information to compute the expected value. Multiply the event times the probability. So $1 times the probability of 9/19, and then we'll add that to the loss of $1 times the probability of 10/19. When you compute that, the result is negative 1/19, which doesn't give us a clear feel for the amount of money. It is approximately negative 0.05263, about a nickel. The expected value of the gain to the house is a gain of about a nickel, and to the player is a loss of about a nickel. Example: volunteers working to raise funds for a new community library sold 1,000 raffle tickets at $10 each. These tickets are to be randomly drawn and prizes are awarded as follows. 1 prize of $1,000, 20 prizes of $50, and 100 prizes of $20. A. What is the expected value of this raffle to you if you just buy 1 ticket? Let's set up a table to write down our winnings or loss options. I'll start by labeling the first row as gain or loss and right below it the corresponding probability. If you win $1,000, you'll get $1,000 at the winning, but guess what? You don't get the $10 you paid for the ticket back, so your actual gain is $990. There's 1 such ticket, so the probability is 1 out of 1,000. If you win $50 or a $50 raffle, you actually only win $40 because you paid $10 to play the game. There are 20 such tickets. And if you win $20 or you get a $20 raffle, you actually win only $10 because you paid $10 to play the game, and there are 100 such tickets. If you just played and didn't win at all, it cost you $10, and the probability that you don't win is the total number of tickets minus the sum total of all the winning tickets. You have 1 that wins 1,000, which is $990 for you, 20 that wins $50, which is $40 for you, and 100 that's a $20 raffle prize, but it's a $10 win for you. So, of the tickets that don't win, the probability is 879 out of 1,000. Now let's use our expected value rule to compute the expected value. We take the outcome, which is $990, and multiply it by the probability of 1 over 1,000. Take the outcome of 90 and multiply it by the probability of 20 over 1,000. Take the outcome of $10 and multiply it by the probability of 100 over 1,000. And take the outcome, you just bought a ticket but didn't win, that probability is 879 out of 1,000. You can use your calculator to do this arithmetic. The result is -6. The expected value of this raffle of buying 1 ticket is a $6 loss. Part B. What is the expected value of this raffle if you buy all the tickets? Well, the expected value if you buy just 1 ticket is a loss of $6. And if you buy all 1,000 of them, then the expected value of them all is 1,000 times -6, or a total loss of $6,000. Example, a man wishes to purchase a 5-year term life insurance policy that will pay the beneficiary $25,000 in the event that the man's death occurs during the next 5 years. Using life insurance tables, he determines that the probability that he will live another 5 years is 0.96. What is the minimum amount that he can expect to pay for this premium? The minimum premium occurs when the insurance company's expected profit is 0. Let's identify some events. We'll let A be the event he lives the next 5 years. The life insurance tables told him that that probability is 0.96. So the complement of he lives the next 5 years is that he does not live the next 5 years. Then the probability of the complement would be 0.04. Just a quick reminder, the probability of an event added to the probability of the complement of that event is 1. What we are looking for is his premium payment. So let's let X equal the premium. That's what we're solving. We'll set up our expected value tables. We have an outcome and the probability associated with that outcome. One of them is he just pays the premium. And the probability is 0.96 that he pays the premium and he'll live the next 5 years. The other outcome possible is a $25,000 payout, but it's minus the premium payment. And the probability of that is 0.04. Before we continue, let's just take note that we are looking for an expected profit of 0. We now have the information we need to get our expected value. So we'll say E equals, we'll multiply the possible outcome by the probability. That's negative X, that's the expense of the premium multiplied to the probability that this man lives the next 5 years. And we'll add that to the $25,000 payout minus the premium payment, and we'll multiply that to the probability that he does not live the next 5 years. When we are looking to find the minimum premium, expected value should be 0. And so we'll set the negative X times 0.96 plus 25,000 minus X times 0.04 equal to 0. We'll do a little bit of algebra. Multiplying the first two terms together, that'll be negative 0.96x. Now, for the 25,000 minus x times 0.04, we distribute that 0.04 to both terms. 25,000 times 0.04, that's 1,000. And then we distribute the 0.04 to the minus x, which would be just minus 0.04x. Let's rearrange some of these numbers. We'll have 0 is equal to 1,000, and then let's combine the like terms of negative 0.06 with negative 0.04, both x. Added together, that's just minus x. Add x to both sides, and when solved for, you get x equals 1,000. What does this mean? It means that the minimum premium he can expect to pay is $1,000.